In May 1987, a National Timber Bridge Conference was held in State College, Pennsylvania. The conference was driven by one major thought. Bridge repair and replacement will be the biggest single expense for our highway system for the foreseeable future. A minimum of $20 billion worth of bridge repair and replacement is needed. The conference looked for means and methods to reduce that staggering figure. They asked, timber bridges, are they tomorrow's bridges? To answer that question, let's begin with that 1987 conference, look at what was accomplished then, what has occurred since, what is ongoing, and what are the future plans and implications. As part of the 1987 convention activities, a 48-foot, two-lane timber bridge was installed in the nearby community of College Township, Pennsylvania. The bridge was of a post-tension design, built of western Douglas fir, installed under the supervision of Wheeler Consolidated, the manufacturer of the bridge. But more importantly, it was constructed by the municipal employees of College Township. That answered an important question. Would the cost savings associated with timber bridges be diminished by the need for professional construction forces? The answer was obvious. Modern timber bridges could be constructed efficiently by municipal workforces. Other concerns were raised at the convention, and many have since been formally addressed. Take the area of materials and design. First, materials. Pennsylvania has an extensive growth of second-generation hardwoods, white oak, red oak, maple, but this material was not being used effectively. Rather than used for construction, hardwood products were furniture-oriented, chiefly marketed as high-quality veneers. The stumbling block was that the material had never been approved for construction using modern design stress values. In 1988, design stress values were produced and approved, and a short video program titled Hardwood Anyone was distributed to encourage the use of Pennsylvania's hardwood products. With approved design stress values in place, modified and totally new bridge designs began to surface. Primary among them were the longitudinally stressed laminated deck, the stress laminated hardwood steel composite deck, and the glued laminated structure. The Pennsylvania Department of Transportation produced videos, held seminars, workshops, and a national teleconference to alert interested users to the economic possibilities of modern timber bridges that can have lower cost, be locally constructed, be in harmony with the environment, and be aesthetically pleasing. But did they work? Even as construction on the College Township Bridge was being completed, testing procedures were begun. These initial tests showed bridges of this type, pre-stressed at the time of installation, will retain a significant and adequate amount of that pre-stress. The moisture content of the timber had little effect on the pre-stress. Some loss in camber was noted. One negative aesthetic aspect did surface. The anchor plates crushed into the timber ends. This is a detraction from the bridge appearance and is not a safety issue. To eliminate that, larger anchor plates are called for in future installations. But to paraphrase the poet, a single test does not a bridge design make. In 1989, the U.S. Department of Agriculture came back to the College Township Bridge and conducted further tests. Initial inspection showed the asphalt wearing surface to be in excellent condition, despite the recorded sag. The bridge had sagged an additional 9/10 of an inch since a 1987 test. Again, aesthetic, but not a safety factor. To measure deflection, a grid was set up on the underside of the bridge. using string lines and metal scales with mirrors. The test vehicle was a 10-wheel dump truck, weighted at 54,000 pounds, placed at 2 predetermined positions. The first test was with the bridge unloaded, then with the truck on the bridge, unloaded again, the truck at the second position, and finally unloaded again. The overall positive test results showed that modern timber bridges appeared to be practical, but further demonstration projects were needed. To effectively measure that practicality, the Pennsylvania Department of Transportation embarked on a demonstration timber bridge program. 17 projects were approved for timber bridge construction. These projects involved 13 townships, 2 cities, 1 borough, and 1 county. The demonstration timber bridge program had 2 major phases. Phase 1, design, supported by 80% state funding and 20% local funding. Phase 2, construction, had a wider base. 80% from the Pennsylvania Bridge Bill, 10% from the U.S. Department of Agriculture Forest Service funds, and 10% local funding. 3 bridge designs were approved based on the length of the opening. For 20 to 24 feet, the longitudinally stressed laminated deck. For 25 to 45 feet, the hardwood steel composite deck, and over 45 feet, a glued laminated structure. Regardless of the bridge type, the design criteria included such items as restrictions on allowable deflection and skew, acceptable and preferred load ratings, use of timber in substructures and rails, and all timber to be hardwood. All 3 of the new bridge designs profited by the College Township experience. Let's begin with the hardwood steel composite deck, designed by Ralph Mozingo of Pennsylvania State University. The installation of this demonstration bridge was in Clarion County, Pennsylvania. It is a single span, 42.2 feet in length, 23.85 feet wide at center line with 2 traffic lanes. The timber laminations are red oak, 2 inches by 16 inches, creosote treated. With every 5th lamination, a steel plate 3/8 of an inch by 16 inches. There are 14 full-width stressing rods, spaced every 36 inches, each with a steel bearing plate. The designer felt that the use of hardwoods and the inclusion of the steel plates would reduce the deflection values found in the College Township Bridge. New ash-toe bridge designs call for deflection values of L over 500, or the span over 500. The College Township Bridge is 48 foot in length. That, over 500, would give you an allowable deflection under the new bridge criteria of 0.096. The College Township Bridge deflection was 1.96 maximum. Unlike the College Township Bridge, which was assembled off-site, the Clarion Bridge was assembled on falsework. This was done to provide access for the workers as well as to maintain camber in the deck. The falsework was fully removed prior to any testing being done. Another difference is that this bridge had timber abutments and end walls placed 2 feet below the scour line. The Clarion Bridge stressing rods were full length, again unlike the College Township Bridge where the rods were coupled. That coupling contributed to the visible movement of the deck as stress was applied to the rods. At Clarion, when stress was applied, no visible movement could be seen. The Clarion Bridge installation also used a smaller-sized crane. At At College Township, the bridge sections were assembled off-site and lifted in place. Some theorize that this contributed to the camber loss. However, given the evident difficulty in aligning the sections at Clarion, some off-site assembly may be warranted for bridges of this type. Stress rod alignment was a constant concern. Even though the pre-drilled holes in the timber were 3 inches in diameter and the rods had guide sleeves. But eventually, despite the weather, the rods were inserted and stress was applied. Before stressing, the laminated steel plates gave the deck a wavy appearance. After stressing, this wavy look disappeared. The workers began removing the falsework in preparation for the scheduled tests. The bridge rails were installed and the remaining falsework was removed. This was the first bridge of this design to be installed, so interest in the test was high. Representatives from Penn State University, the Pennsylvania Department of Transportation Local Roads Program, test administrators from the Constructed Facilities Center at West Virginia University, and the Forest Products Laboratory of the U.S. Department of Agriculture, along with local municipal officials, were on hand. The testing done at College Township utilized a string line and mirrored metal pieces. At Clarion, 4-foot metal rules, pre-drilled, were placed at predetermined positions. The positions were such that by using a zero string line, you could get a visual impression of the bridge profile, in effect, a camber profile. Additionally, metal clips were attached to the bridge for moisture tests. They were left in place to ensure that future readings will be taken from the same locations. The planned tests would use 2 triaxle trucks, weighted at 62,000 pounds apiece. Each truck was weighed by a motor carrier enforcement team from the Pennsylvania Department of Transportation. Scale readings were taken and recorded for each load-bearing axle. Test measurements were taken with the bridge unloaded, with one truck in position A, with the second truck in position B, with both trucks positioned on the bridge, and finally another test with the bridge unloaded. The test data is currently being analyzed, but initial indications are the bridge meets all design criteria. As the Clarion Bridge was being completed, glulam beam testing was being conducted at the Pennsylvania State University Agricultural Engineering Department and School of Forestry. Beams of this type are to be used in the construction of a glued laminated structure in Ferguson Township, Center County, Pennsylvania in September 1991. Both treated and untreated pieces are being tested. Timber Bridge Update number 2 will detail the test results from Penn State University, the installation and testing of the glulam structure at Ferguson Township, and the installation and testing of the longitudinally stressed laminated deck to be installed in Cherry Township, Sullivan County, Pennsylvania. Timber Bridge Update number 2 will be released in November 1991. The 17 projects will be monitored for at least 3 years, not only to measure the design and construction, but to help determine maintenance requirements. Are timber bridges tomorrow's bridges? As signs like this appear, more and more municipal governments will ask that question. As municipal governments address their bridge needs, more and more will look to modern timber bridges for relief. And the Pennsylvania Department of Transportation, the U.S. Forest Service, and dozens of professional engineers and researchers will be providing the answer. For further information on PennDOT's Timber Bridge program, contact the Office of Research and Special Studies, Pennsylvania Department of Transportation, Room 905, Transportation and Safety Building, Harrisburg, Pennsylvania, 17120, or call 717-787-6376.